Because Bezout's identity is so important to us as we progress in abstract algebra, I wanted to give an example of proving a very well-known result with Bezout's identity used to give you an idea of how that identity can be helpful to us. I wanted to give you some information about Bezout or maybe Euclid, since that's what we're going to be working on next, but it's actually very difficult to find anything interesting on the internet about either of those people, so I gave you SpongeBob instead with the idea that Bezout is magic, because that's absolutely true. We're going to use this lemma that frequently. It's a really good one to have at the tip of your fingers as soon as you see an assumption that two numbers are coprime. So the lemma that we're going to be proving in these slides, and I'm not going to walk through the proof in an incredible amount of detail. I'm going to leave that for you all to do as part of your work for next week, but I will present you the proof and some of the main ideas of it. Euclid's lemma is a very well-known result. We're going to assume that p is a prime number, and we are going to assume that p divides the product of two integers n and m. The result is that we can conclude that either p divides n or p divides m. Now this is a very special lemma. We use this all the time. If we know that we have a prime number like 3 and 3 is dividing 45, if we think of 45 as 9 times 5, what Euclid's lemma is saying that either 3 divides 9 or 3 divides 5. Remember that an or statement is inclusive. So with that same example, if I take 45 and I think of 45 as 3 times 15, Euclid's lemma is still correct in that sense. 3 is a prime that divides 45, and 3 divides 3 or 3 divides 15. It can divide both of them. That's perfectly fine, but it must divide at least one of the factors. And this is another thing that's useful to us. We may use Euclid's lemma from time to time in abstract algebra, so it's an important result to know, and the proof of it uses Bezout's identity. So let's walk through some ideas of this proof. It's a good proofwriting technique before you begin the proof of any statement to know the definitions of everything involved in the statement of the lemma. If you do not know the definitions of every word that appears in that theorem, lemma, whatever it is you're proving, you're not going to be able to prove it. Mathematicians have a habit of writing exactly what is necessary in order for a result to be true. So if you don't know what you're assuming, you're missing information and you're not going to make it to the end. So before you start walking through the proof of Euclid's lemma, you should at least make sure that you understand what it means for a number to be prime, that you understand what it means for one number to divide another, and that you understand the greatest common divisor of two different numbers. That's not immediately obvious from the statement of Euclid's lemma, but given that we're going to be using Bezout's identity, which deals with the greatest common divisor of two integers, we know that as sort of a hint before we start the proof. We should make sure we understand that definition of greatest common divisor as well. The next thing to feel comfortable with before we start the proof of this is a technique you might have learned in discrete structures, which is we're trying to prove a conditional statement. P implies something. So P is a logical sentence that we are assuming as the if part. We need to draw the conclusion Q or R. How are we going to go about proving this? Because it doesn't really matter the specifics of the statement of Euclid's lemma. We should have some general ideas about how do we prove things that have this particular form. Whenever you're proving a conditional statement, if this holds, then we conclude this, you always assume the antecedent, the part that comes on the left-hand side of the implication. So we get to assume the P. We then need to show what's on the right-hand side of that implication, that Q holds or R holds. So what we can do is break symmetry here and gain an extra assumption. We may also assume, and here I'm going to say, without loss of generality, that Q is false. Because if we're trying to prove that an OR statement holds, and one branch of the OR statement we know to be true, then the whole OR statement is true. So we can make the additional assumption that one of these two things is false, In a general proof, it might be more helpful to assume that one of these things is false over the other, but we have symmetry here. Our OR statement is that P divides N or P divides M. N and M are totally arbitrary, so our Q, which is P divides N, and our R, which is P divides M, they're entirely symmetric, and so it does not matter at all. There's no loss in any amount of generality in just picking one of them at random and saying this one does not hold. Once we've made that additional assumption, it's our job then to prove that R must hold. So if you take a look at the proof that I've written up here for you, and I'm going to leave that proof up here for a minute so you can pause it and take a look at as much of it as you'd like. We assume the if part of our statement, which is that P divides NM. Then the very next sentence that I have in my proof is that W log without loss of generality. I'm also going to assume that P does not divide N. And that gives us extra ammunition and extra assumptions and is a valid logical thing to do from the perspective of this proof. So that's how the proof starts out. Our first two statements are assumptions. The first part is a given to us, and the second part is coming from the specific format of the type of thing that we are proving. And then it becomes very clear how our proof needs to end. Our proof needs to end by showing the R part of this general form. An exercise that you're going to have to earn community points this week is I've copied this proof and numbered the lines one by one and put it into our course log. Your job is going to be to color this proof. So for each line in this proof, go back and look at the videos on doing proofs in color and attribute a color to each line of this proof. And feel free to talk about that and discuss that amongst yourselves. And then I have a couple of questions about larger statements about why something is part of this proof in general. Like, why is this line necessary? Why do we have to do this? Like, couldn't we omit this part of the proof, etc.? And so reading through this proof and having a discussion about it is part of what we're going to have to do this week. The last thing that I'm going to do in this video is just walk you through the next two lines of this proof, because that's where the application of Bezout's identity comes in. So we are making this additional assumption that P does not divide N. And then what we want to do is consider the GCD of P and N. Although when we have a prime number and any other number and we look at this GCD, there's no guarantee that this GCD has to be 1 just because this is prime. Remember, we had an example with 7 and 28. But because primes don't have very many divisors, there really are only two choices as to what this GCD can be when one of these numbers is a prime. This GCD either needs to be equal to the prime or it will be equal to 1. And because we get to make this assumption that P does not divide N, we know that P is not a factor of N. And because P is prime, the only other thing that this could be is equal to 1. So that's the key assumption, and then Bezout's identity gets applied where we take 1 and write it as this integer linear combination of P and N.